right now we're finally going to cover board cutting. So you had a couple examples that you could work on previous homework assignments. Here we're going to describe an algorithm we can go through. Well, let's just look at this example first. Suppose you have a job that requires the following boards. So we have two 8-foot boards, one 7-foot, one 6-foot, two 5-foot, three 4-foot, four 3-foot, four 2-foot boards. And here it says use the first fit algorithm to determine how many 9-foot boards you must buy. So before we describe this first fit algorithm, let's remember a little bit recall a little bit about Hamiltonian circuits. So in I believe it was week 2, we discussed the nearest neighbor algorithm and the sorted edges algorithm. And both of those were designed to help find a minimum cost Hamiltonian circuit. Now, there is no algorithm which definitely finds a minimum cost Hamiltonian circuit. It's actually a very difficult problem in math, and many mathematicians think that there will never be an algorithm which allows you to find a minimum cost Hamiltonian circuit. Similarly, for a problem like this, so with small numbers like these, we can see that we could figure out a minimum number and we can interpret whether it makes sense. But in general, there is no algorithm that we can use to find a minimum number of, in this case, boards we must buy. Now, problems like those, this problem and the problem of finding a minimum cost Hamiltonian circuit are equally difficult in a sense, and they fit under a category of math problems called NP hard, letter N, letter P hard problems. And logically, if an algorithm exists which finds one, or if we can find an algorithm that solves one type of an NP hard problem, then it can be modified to find an algorithm for all NP hard type problems. Now, you don't need to know anything about that NP hard, but do know that there is no algorithm which guarantees we can minimize the number of boards that we must buy, just like there was no algorithm that guaranteed that we could find a minimum cost Hamiltonian circuit. But we will describe the first fit algorithm. There are a couple other algorithms we're not going to cover. I think the first fit, well, technically the first fit decreasing. I think this is the nicest algorithm. It makes the most sense. But if you want to look at a couple other algorithms, you can look at pages 97 to 98 in the textbook for other algorithms. I'm not going to test you on the other ones. I'll test you on this one. So let's see how we're going to go about doing this. Now, first, I will always give them to you in decreasing order, meaning starting with the longest board and going to the smallest. Some of the algorithms don't assume that, but then it says, we'll put them in decreasing order because it makes it so that we're going to have less, empty space. But let's see how this is going to work. Now, in the textbook, this is in a section called bin packing, and an equivalent problem would be you have a bin that holds 9 things, and you have a thing which takes 8. Well, you have 2 things which take up 8 of those 9 spaces, and so on. I like the board cutting visual more because it actually lets you think of, well, I have this board, I'm going to chop off a hunk, and so on. So I always like the board cutting. So how are we going to do this? Well, I like drawing out the boards. These are 9-foot boards. I'm just going to mark off a 9 over there. Now, how are we going to do this? Well, another thing I like to do is just list out the boards we have. So under here, I'm going to go 8, 8, 7, 6, 5, 5, 4, 4, 4, 3, 3, 3, 3, 2, 2, 2, 2. Now, I like to do that because it allows me to cross them out as I'm going along instead of just, counting. So the 9, we have 9-foot boards, and underneath that we have the boards we need. Well, first we need an 8-foot board. That'll go there. We can't fit another 8-foot board there, So we'll go to a second board. So we've used both 8-foot boards. Now, the next we have is a 7-foot board. That's not going to fit on any of the first two. Those two gaps on the first two are just 1 foot. But here we can put the 7-foot board on a third board. Next, we have a 6-foot board. That's not going to fit on either of the first two or any of the first three. So we need to go to the next board. And similarly for these two 5-foot boards. So that gap on the 6-foot board is 3 feet. A 5-foot board is not going to fit that. So we're going to need to go to 2 more boards for these 5-foot boards. Now, what about the 4-foot boards? Well, this algorithm says we're going to try to fit it on the first board. And if it doesn't, we're going to try to fit it on the next board. And if it doesn't, as you keep going through, then you're going to make a new board. So this first 4-foot is not going to fit on the first 4 boards, but it will fit up here because 4 plus 5 makes 9. This next 4-foot board is also going to go there. And the last 4-foot board, we're going to need a new board for. Well, now we have 3s and 2s. Next, we're going to go to the 3s. The first 3 can go up there on the other side of 6. The next 3 isn't going to fit on the 8 or the 7s. The 8's and the 7, so we can put it here. We're left with 2 feet there. It might be tempting to start filling in 2s. I would recommend against that. So I'm not going to do it. We have 2 more 3s. They're not going to fit anywhere, so we need new boards for the next 2 3s. Well, the last 2 3s. Now we have 4 2s. Now notice it's not going to fit. A 2 isn't going to fit on the 8-foot board because we have only 1 foot left. But a 2 will fit there. A 2 will fit there. 4 plus 3 plus 2 is 9. And we have 2 more 2s. Notice only one of them is going to fit there. And we're left with, what, 1 extra foot there. And we're going to need another board to fit that last 2 on. So here, how many boards must we buy? 1, 2, using this algorithm, 1, 2, 3, 4, 5, 6, 7, 9 boards. And I could also say how much excess wood with this. Well, how much excess wood? We have this excess 1-foot piece. We have this excess 1-foot piece. We have this excess 1-foot piece. And we have this excess 7-foot piece. So that's 10 feet excess wood. Now, you may wonder, this algorithm does give us that answer. You may wonder, well, we have 10 feet of excess wood. Can these be rearranged in a way that would cause us to buy 1 fewer board? So one solution for these types of problems that many of you submitted was, let's add up the lengths that we need and divide by 9. In general, that does not work. And in this example, that does not work. So in this case, if you added up all the lengths, what would you need? 16. Maybe I'll make this a remark. Down here. Remark. Adding the lengths of wood gives how much wood? Well, if we go back to the top, we need a total of 16 plus 7 makes 23, plus 6 makes 29, plus 10 makes 39, plus 12 makes 51, plus 12, 63, plus 8 gives us 71 total feet of wood. We would need 71 feet of wood. Dividing 71 into 9-foot boards would suggest you need 8 boards. But if you buy only 8 boards, all of these pieces of wood are not going to fit. And why won't they fit? Well, that's a much more difficult problem. But, maybe I'll write that. Adding lengths gives 71 feet of wood. So I'll say, but we need more than just 8 boards. 8 boards, if you get 71 feet, divide that into 9, it gives you that you need, what, 8 boards, then you'd have 1 foot of excess wood. But we need more than just 8 boards. Now, why is that? Well, if you look in that previous example, those 8-foot pieces are always going to leave a 1 foot excess. So that last 2, this last board that has a 2 and a 7 foot excess, that last 2 isn't going to fit anywhere in there because there's only, in those first 8 boards, there are 3 extra feet of wood, and these first 2 ones are always going to exist. So that method won't necessarily work. Now, there are some examples where the first fit algorithm does not give necessarily the minimum number of boards that you need. Let's go to the next page. And that's going to take a moment for some reason. Okay, next page. Example. So the same directions, use the first fit algorithm. I'm just going to give you the chart here. So what is this? Number, length, sort of spelled correctly. We need 8-foot board, 7, 6, again, 8 through 2. Now putting 1-foot boards on it isn't, as interesting because 1s fit anywhere. Okay, 1, 2, 1, 1. So we need here 1 8-foot board, 1 7-foot board, 2 6-foot boards, 1 5-foot, 3 4-foot, 5 3-foot, 5 2-foot. And how large are the boards that we're going to use here? I didn't write that down. Why didn't I write that down? Here we're going to use 12-foot boards. Yes, let's do 12-foot boards. I think that was, oh, no, sorry, 8-foot boards. I didn't write on my notes the length, because I wrote the notes in 2 different spots. So we'll use 12-foot boards. So let's use 12-foot boards. No, wait, I'm sorry, 8-foot boards. Sorry. I just did this example 15 minutes ago. I can't remember what I did. 8-foot boards, that is right. How many are we going to need? Well, again, I'm going to list out the boards. We need an 8, a 7, we need 2 6s, we need 1 5, we need 3 4s, we need 5 3s, and we need 5 2s. And again, I'm going to draw out an 8-foot board. This is 8 feet. So first, the 8 is going to fit perfectly. What about the 7? Well, the 7 will go here, and there's going to be 1 foot of excess, which we'll deal with in a moment. 6s and 5, we're going to have to give their own boards, because a 5 is not going to fit on a 6. Let's move the cursor so it's not in the way. I'm not even sure if the cursor records. So we have our 8, 7, 6, and 5. Now, what about the 4s? Well, we have 3 4s. 4 is not going to fit on any of these current boards because we have only 8 total feet. They're not going to have, none of them have 4 feet of excess, but we can put a 4 here, and that gives us another 4-foot piece up there, taking care of 2 4s. Third 4, we have to go on to the next 4. Now we have 3s. How many 3s? We have 5 3s. Well, the first one can go on that one, because 3 and 5 make 8. The next one can go here. That takes care of 2 of the 3s. And we have 3 more 3s. Well, 2 of them can fit there. And then we'll need another board. So that takes care of all 5 3s. And now what do we have? We have 5 2s. So a 2 can fit there, a 2 can fit there. On this 1, 2, 3, 4, 5, 6. On this 7th written board, one with the 3 and the 4, a 2 isn't going to fit because that's just 1 foot. So we can't put it there, but on the next one with 2 3s, a 2 will fit. So there's 1, 2, 3, and we need 2 more 2s. They'll fit here. That takes care of all 5 2s. How many boards? There's 1, 2, 3, 4, 5, 9 boards. And how much excess wood? And again, we're using the first fit algorithm here. With how much excess wood? Well, we have this 1 foot piece, we have this 1 foot piece, and we have this 1 foot piece. So with 3 feet of excess. And because these are 8-foot boards and we have 3 feet of excess, that does tell us that the first fit algorithm does give a minimum number. So in previous example, first fit gives optimal solution because the excess is less than 8 feet in that case. But what if we adjust this a little? This next example will not give the optimal solution. We will be able to find an optimal solution relatively easily. So let's do this next example. Same as before, previous one, except use 6 2-foot boards. So same as before, except we'll use 6 2-foot boards. Now, how does that change? Well, everything up to the 3s is the same. So I am going to have to redraw this. So I'm just going to redraw everything as it was until the 3. So how many did we have? We have 9. So it's the same as before. We had an 8. These are 8-foot boards. We had a 7. We had a 6. We had another 6. We had a 5 and a 3. We had a 4 and a 4. We had a 4 and a 3. We had a 3 and a 3, and then the last 3. So this is, everything is the same, except now we're using 6 2-foot boards instead of 5 2-foot boards. So it brings us to the same spot we were in the previous one after dealing with the 3. But now we have 6 2s to deal with. So I'm going to write out 6 2s. And where can we place these 6 2s? Well, we can place one up there. On the other side of the 6, we can place another up there on the other side of the 6. Where can we place the next 2? Well, on this one with 2 3s, a 2 is going to fit. How about the last 3 2s? Are they going to fit here? No, they won't. 2 of them will fit there. But that gives us 1 foot of excess. And then that last 2 is going to have to go on its own board. So how many boards does this use? Here, first fit yields, maybe I should say gives, that's what I said before. Gives how many boards? What is it, 10 boards? 10 boards with how much excess? Well, there's this 1 foot piece of excess up here, this 1 foot piece of excess, this 1 foot piece of excess, and this, that's not 7, 6 foot piece of excess. So with 9 feet of excess. Now, just because we have more excess than a length of a board does not imply that it didn't give the optimal solution. So it depends on how the lengths of the boards fit. And right here is where an algorithm, well, right here is why there is no efficient, well, there is no known algorithm for finding the minimal number of boards. In this case, so I'll write this, I have a little more space at the bottom of the page. In this case, there is an arrangement which uses only 9 boards. So with these numbers, there is an arrangement. In general, there may not be. So what arrangement would work here? Well, I'm not going to tell you. I may mention this on Thursday of this week. I may mention it Thursday of last week, but it's a good exercise. Try to find another way you can arrange these that uses only 9 boards for this example with the 6 2s. There is one. Yes, there is one. And in that case, there would be only 1 foot of excess wood. So try that. That's a useful exercise to go through. But we've covered board cutting applications, let's look at one more type of application that this could be. Why didn't that go to a new page? Okay, now it did. Let's look at this next example. A radio station has the following advertising ad lengths, I should say. A radio station has the following ad lengths and the following numbers of ad lengths. So let's put them in a chart again. Number and time. So it has a 100-second time slot or advertisement, a 90-second, well, two 90-second advertisements, one 80-second advertisement, one 60-second advertisement, two 50-second advertisements, two 40s, two 30s, and a 20-second advertisement. So it has all of these lengths, and the radio station says, where should I write it? I don't have much room here. Would using 120-second, 110-second, or 100-second, what's the word, advertising break. So would using, so this is, which of these three will be better? Would using 120-second, 110-second, or 100-second advertising breaks? I should phrase this question slightly differently. I'm sorry. Which of those yields the least dead air? Dead air and radio air, there's no noise. So sorry, which of these three yields the least dead air? And we're going to do this using a board cutting reasoning. So we have three different things to consider: 120-second, 110-second, 100 seconds. Let's do 120-second first. So again, we're trying to fit things within or in a 120-second block. Let's draw a board of 120 seconds, and let's fit in all the numbers. I'm going to put the numbers at the bottom. So we have 100, we have two 90s, we have an 80, we have a 60, we have two 50s. Oh, that's a good job there, two 50s. 50, 50, 40. I almost wrote 44 last time too. 40, 30, 30, and 20. And let's fit them in 120-second time slots. 100. I'm actually not going to cross these out. Well, maybe I will. 100, 90, 90, 80. 60 isn't going to fit anywhere. So there's a 60. Now how about 50? 50 will fit up here. A 50 will fit there. We're left with 10 seconds. But the next 50 is going to have to go into another block. Two 40s, well, the first 40 is going to fit on the other side of the 80. And the next 40 is going to fit with the 50. And now we have two 30s. Well, look at this. 30s fit perfectly in the 90s. And a 20, which fits up here. So right here, with 120 seconds, how much dead air is there? Well, the first four blocks are completely filled. This next one has 10 seconds of dead air. This has 30 seconds of dead air. So this, using 120-second advertising breaks, gives 40 total seconds of dead air, and they're going to need 6 advertising breaks. So now I'm going to have to go to a new page, but let's do the same thing with 110 and 100. And let's wait 5 seconds for the page to change for this Technology, for some reason, gets slow when it's an entire year old. So here we have 110 seconds, and what were our lengths? We had 100 second. You could chop off zeros from everything. I'm not going to. And my instinct is to just get rid of zeros from everything. So we're dealing with smaller numbers, but I am gonna leave them. Okay. I guess when I'm thinking 250s, I write 55. So now we have 110 seconds. Well, first, a 100 is going to fit there. The 90s are going to have to go on their own. The 80s, well, the 80 is also going to have to go over there. The 60 is going to go here. Now, what about 50? A 50 is going to fit perfectly on the other side of that 60. And the other 50 is going to have to go on the next block. Now, how about two 40s? Well, a 40 isn't going to fit anywhere, or isn't going to fit in those first four, because 80 plus 30 gives 110, 90 plus 20, and 100 plus 10. But a 40 is going to fit on the other side of that 50. So that used one of our 40s. Now we have to use the other 40. We have two 30s. A 30 is going to fit on the other side of the 80, and a 30 is going to fit with that 40 and nowhere else. And how about 20? Well, a 20 is going to fit there. So with 110 second advertising breaks, we have how much dead air? Well, 10 seconds plus 20 seconds gives 30 seconds, plus another 20 seconds gives 50 seconds, plus this last gap is 50 seconds. So how much dead air? Maybe I'll write out all these numbers. Dead air of what? 10 seconds plus 20 seconds plus another 20 seconds plus that last one has, what was it, 40 seconds, gives 90 seconds. So right here, the 120 second advertising blocks work better than the 110 seconds. But how about 100 seconds? Let's check that. And here I am going to cross out the numbers. 100 fits perfectly. The 90s are going to have to go on their own blocks again with 10-second gaps. And even right now, you could fill in that these are going to be gaps. It's technically not perfectly in keeping with the first fit algorithm, but you could do that. There are no 10s. An 80 will go there. A 60 is going to have to go on the next one. And two 50s aren't going to fit anywhere that we have, but we can fit them in the same 100-second block. How about 40s? Well, a 40 is going to go on the other side of 60, and another 40 will need its own block. And how about 30s? Well, 30 won't fit on that 80, but two 30s will fit on okay, I was just comparing this to my other example. Two 30s will fit on that 40. Two 30s fit perfectly on that 40. And then this last 20 is going to fit on the other side of that 80. So here, the dead air, everything added up perfectly except those two 90s. So this has dead air of 20 seconds. So comparing all three answers, what was it with 120? 40 seconds, 90 seconds, 20 seconds. So what was the actual question that was asked? Which of them yields the least dead air? Well, we'll just conclude 100-second advertising breaks gives the least dead air. Gave 20 seconds using the first fit algorithm. So there are many types of applications, these board cutting or bin packing problems. You could do something with, you need certain lengths on a bookshelf. You need, certain rows in a garden, like 10 feet of celery, 10 feet of corn or whatever. But the logic behind all of them follows the same way as the board cutting. And definitely observe in that one example that you can't just, I think it was the first example, you can't just add all of the lengths together and divide and have it fit perfectly. Yeah, that was the first example. So try practicing this one. I may mention something about it during next week's workshop as